Okay, your talking head is back. All righty. So I see lots of, oops, what was that? Something happened on my computer, but I guess I'm okay. Can everybody hear me, Casey? Good. Um, so far, I see Casey and Cindy. Thank you. I do not see Brandon, Nicholas, Book, Mina, Michael, Taryn, or Solomon.
I'm here. I'm here.
Oh, I know you're here.
Oh.
I know you're here. I just
Sorry,
can't
I'm cooking
see.
some eggs real quick. Can't
Oh
quite
my
show it.
gosh. You're cooking some eggs and playing around a Team Fortress and
Uh-huh.
and uh and talking to your girlfriend and
Yeah, I'm terribly sorry.
I'm just joking with you. All righty. I'm gonna try to get on with things then. I had some trouble with my monitors this morning, so I'm gonna be a little bit goofy for a couple of minutes. I got to get everything. I had to restart my computer, only to learn that it was my um, that it was actually my television that was talking to me. I have a television monitor in my office. It's a big old, like, I don't know, 30 or 40-inch TV or something. And uh, it there was this message in the middle of my screen, and I couldn't tell whether it was my camera talking to me or what. And I couldn't get the mouse to go over it. I couldn't make it go away. So I restarted the computer, and there it was again. But it's the friggin' TV talking to me. Update from my TV. My TV does not need updating. Goofball. Okay, so where were we? Let's see here. Going to share a screen. Okie dokie. So I'm assuming y'all can see the PowerPoint, right? And there's a bunch of information flying around here, and I'm gonna try to summarize it in a moment. But this is, I think, a pretty confusing way to look at it. But I'll use it, and then I'll give you some homegrown information. So this green thingy here is a depiction of a diffraction grating. Pretty inaccurate, but anyway. The main operative thing about diffraction gratings is that they have this regularly repeating array of things, right? They're called blazes. This is one blaze of a grating, for example. And the spacing between them is the same, right? And just to freak you out a little bit, when you look at a grating, you don't use Snell's law to calculate what you're seeing. So, for example, if you had light coming in from this direction, and it hit a blaze like this, you would expect the takeoff angle to be, like, if that's alpha, then we'd have alpha up here, right? But that's not the way they work. They basically they work more along the lines of scattering, right? Where every ray scatters off every point on the grating. In order to calculate the properties, essentially the wavelength of the diffracted light, at that pair of angles, alpha and beta, then you have to use the grading equation. So I really miss having a demo of this, but I have a big grading. And I have folks look at the overhead lights, the fluorescent lights with the grading, and you can turn it at different angles and you can see the light at different angles. There's like 3 or 4 angles. And you can set it to one angle and you'll see the light, but it's colored blue. Another one is colored green. Another one is colored yellow, right? And it's funny because none of those angles that you look into the grading happen to are the specular reflection angle, right? If you used a regular mirror, actually, you can see the white light reflection if you look in this mirror-like grading surface, right? When the angle of incidence equals the angle of reflection, right? But more commonly, if you look off that angle, you'll see, oh my gosh, there is the overhead lights in red and they are in blue, right? So it copies this reflection, but in a different color. And that's because when you have these regularly spaced scattering centers, you can get odd phenomena happening, right? So there's a couple of things that go into this phenomenon, and one of them happens to be these two angles here, alpha and beta. Like these are the normal angles that you would use to calculate how you would see a reflection, right? So these are called the Blaise angles, right? And it just so happens that gratings are most efficient when alpha equals beta. Not a huge surprise there, right? When the angle of incidence equals the angle of reflection, then the gratings actually work better. But they only work for a particular wavelength, right? Since the Blaises aren't flat, you as an observer, if you were an observer far from this, you'd expect alpha to be here and beta to be way off here, right? Because this is like a flat surface, and alpha's coming in. But really what alpha equals alpha, you would see something, it's sort of like a little periscope or something, it would shine off at a different angle, right? It would reflect at a different angle. So, this is one aspect of the reflection off a grating here, and I'm gonna make a note of that on my document camera. So beta. Okay, so the alpha equals beta angle constraint is the best one, but it's rarely fulfilled, right? So now let's completely forget about that, right? Now we're going to look at this confusing piece over here, right? And I'm going to try to simplify it as best I can. And now I'm going to go to my document camera here, if I can. There we go. Okay, come on, focus, focus, focus. There we go. So the other aspect of this is that there needs to be 2 points. For every blaze on the grating, you can think of as a single point for scattering, right? every groove, every blaze, every point on the grating that repeats, right? You can think of as just a repeating point here. So there'd be another one out here, right? Another one over here. But what we're going to do is we're going to look at this pair, and we're going to consider light coming in. So here, this is the grating down here. Let's look at a reflection grating. Right. All right. Now, so if light is coming in, looking for a little straight edge here. Light is coming in at this angle here, right? There's light coming in. And then light is also going to come in at that same angle, but over here, right? So we're going to look at parallel rays here. So now what happens is that this point relative to this point, there's a difference in the distance that these rays travel to get to the grating, right? And so you can calculate that difference by going to the right angle to this ray, right? Like I'm doing here. And you can see then, oops, you can see then that these rays are coming in phase up to here, right? This is how we think of it, right? That there's, there's rays coming in phase, right? This is the electric field vector of the light coming in, right? And then what happens is that in order to get to the grating, this guy has an additional path length, right? So it's going to come in here. And this ray now, this ray now reflects at a different point in its phase. So let me take a little break here, take a second, and ask a stupid question about all this. Does this make perfect sense to you, Cindy? I mean, it's not like it's deep. It's just, and that's a stupid question, but
so far so
okay,
good.
cool. Okay, good. So now, what happens next? So well, here, let's just calculate what this path length difference is. We'll call it delta. I forget whether, let's use a little delta sign here. And we can call this, the sign, we'll call this angle I here. And we'll call this the grating constant, we'll call this D. And that's going to be, D will be this distance here. And so delta, for this angle I here, this is a right angle here, right? So the sine of I is equal to delta over D. It's opposite over hypotenuse, right? So that's delta over the grating constant D. Does that make sense? So it's like if you have this right triangle here, it's kind of flopped over, but opposite over hypotenuse is the sine function, right? So the sine of the angle I here is equal to delta over d. And this is really how you go about computing the angles that diffract at a given wavelength from a grating, right? So I don't really want to complicate this diagram too much because it's already super busy. But let's take this guy here, right? And I'm going to say delta is equal to d times sine of I, right? Oops, I got that off camera, right? Delta is d sine I, right? Now, there's also a similar, basically an identical process that happens for outgoing rays, right? You know, for outgoing parallel rays, right? And for the this is the incoming. And then this is, you can call it, you know, delta I, right? And then delta O, or call it delta R. That's equal to D times sine of R, right? They're similar, but you know, there's just a different angle involved, right? And so now this guy will have the longer path length, and we'll do the same kind of thing here, but this is sort of the outgoing ray. And if we add these up, we can say that the total path length difference delta is equal to D times sine I plus sine R. Oops. Gotta scooch this guy up a little bit. So now this is just a sort of a generic way to look at a grating, right? Way to calculate path length difference from points on a grating surface. But if you want to see when you will see bright light from a grating, it's when this value here is equal to an integer times the wavelength of light. So when delta is equal to d sine I plus sine R, well, this is always true, right? But when this value here is equal to n times lambda, where n is any integer, and n is typically 1, but sometimes you use higher orders. It's for high resolution work, you use higher orders, but n is typically 1. Then it's like saying that when n times lambda is equal to d sine I plus sine R, then the diffracted ray at I and R is bright. And so, and then when there are many, when there are many blazes, right, or grooves, then only at n lambda is equal to d sine I plus sine R is diffraction observed. So so that's basically how diffraction gratings work. I mean, this is a first order approximation. It's all I know, you know, but I think this is a decent way to start with how they work, right? Okay. So let me change my share here. So when you have a when you well, let me start here. This is a Cherny-Turner type diffraction grating system, right? There's a source, a slit, a collimator, a grating, another focuser, and then an exit slit and a detector, right? And the pair of slits produces high resolution in this case, right? So if you have a light source here, then by making this slit small, you can really take advantage of only rays that are right along this trajectory, you know? And therefore you can collimate that beam very well out here. And then what you do is you just place the grating onto it's called a sine bar or something like that. And the sine bar will allow you to rotate the grating. And then, so you can change the I and the R value. The I value changes as you rotate the grating, as does the R value for this slit, right? Now there's another way to change the R value, which is simply to translate around on this plane, right? So if you could move the slit, then you could see different wavelengths, lambda 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, like that. You could see different wavelengths along this focal plane. And in fact, if you have a white light source out here, a broadband light source coming in, it's going to bounce off this guy, bounce off this guy. Then if you just put a white piece of paper right here on this focal plane, you'd see a perfect little rainbow along that focal plane, you know? And that perfect little rainbow would have a copy of the spectral power distribution of the source. And there'll be some effects from the grading, etc. But you'll get a spectral power distribution in the form of a rainbow here at the focal plane. And so either you can use a slit, right, and a detector, or you can use an array of detectors along this focal plane. If you use a single slit and a single detector, then what you do to change the wavelength is you could rotate the grating. I think for some practical reasons, I think that's easier than moving the slit and the detector. But then as you rotate the grating, you change sign I and sign R. One increases, one decreases. And so you'll get as you change the angle of the grating, you'll get a change in the wavelength that's diffracted at this point. So, and alternatively, you can use, for example, if you have a camera lens, a lot of cameras on this morning, everyone with a camera or a computer or a webcam or whatever, you have, typically webcams are very small chips, right? And they use a strong lens. It's a small, high index, like high radius of curvature lens, and they display the image onto this tiny little, maybe a 1 millimeter array. And if you have 1,000 pixels on the side of this 1 millimeter array, that means you have 1 micron per pixel, which is technologically available. And so in theory, then, if you could create a spectrometer with a spatial distribution out here where the entire spectrum was displayed over 1 millimeter, then you could see you could see this rainbow, or you could see this spectral distribution on your webcam or on your phone cam or on even your camera cam. And so what people in spectroscopy often look for is somewhat larger pixel cameras. So like if you have a 1 centimeter square array, then that makes a really good detector for a spectrophotometer, right? Because you know that, for example, with a typical camera, you can get 30 or 60 frames per second. That is pictures per second, right? So if you took 100 pictures per second, that would be 10 milliseconds per pixel, or 10 milliseconds per exposure, right? Then you'd have, maybe 1 millisecond to read out the whole damn thing, right? So you get 1 million in 1 minute. You have to read out every pixel in 1 nanosecond. It's pretty amazing how quickly these things work, right? But that's not atypical. So, and you'd have to read out the intensity on every pixel, and then translate that into an image. Then that image you'd process down into a line scan, right? And then that line scan would be the spectrum of light that's coming off there. So let's see here. So we'll get back to that in just a sec, but there's a couple of equations that you want to sort of commit to memory here or something. The relative efficiency is the grating over the mirror reflection, right? So if you have a good mirror and you set and it's flat, and alpha and beta are the same, and they're at the normal angles, then you can calculate the grating efficiency at any angle, right? As just a relative reflectivity of the grating, you know. And so if you know, it makes sense if you're going to design a grating to blaze these guys near this alpha equals beta angle, right? But it's not absolutely crucial that you do it this way. These are the two equations that govern the grating. It's n lambda equals d sine I plus sine r, right? Incident and refracted angles, and alpha equals beta, the blaze angle. You know, these are just approximate, of course, because you can't satisfy this and this simultaneously. But when you get close, then you get something that looks more like this, right? If you have a 300 nanometer blaze angle, then the efficiency might be 80% at that 300, right? And then it falls off on either side, you know? And then a 500, 1,000, a 2,000 nanometer blaze, right? So it's just examples of the spectral range of a given grating, you know? And so for a UV vis instrument, you know, you might use a 300 nanometer blaze angle, you know, and then you'll get, you know, out at 1100, you get about a 10% efficiency, which is fine normally. It's not a serious compromise, unless you need every photon out here, in which case you'd use a longer blaze angle. But anyway, these are just design considerations when you talk about monochromator design. Okay. So, oops, oh shoot, what happened? So, so there's a way to calculate the range of wavelengths. It's actually the differential between wavelength and position along this focal plane. And I'll give you the equation there. I'm not sure we're going to use it. That equation is, I like to use d to the -1. And so it's reciprocal linear dispersion is equal to d, the grating spacing, times cosine of r. Oops, not trademark r, the other r. Over n times the focal length of the instrument. So if you have a longer focal length, then you get a smaller d to the -1. And so this, what this means is this is it's d lambda by d theta. I'm not sure if I'm going to be able to do this, but symbols, theta, no theta. Oh. Here, I'll go to symbol. There we go. There's theta. And then what else have we got here? There's lambda. Okay, I'm just going to throw a lambda in there. There we go. Okay, close this guy. So This is reciprocal dispersion. So oops. Anyway, this is supposed to be superscripted, but so so basically normally what you want is a fairly small change in lambda for a given change in d theta, right? So I'm going to take this guy away instead. So and so that way you can define the effective bandwidth of a monochromator as the range of wavelengths that exit the detector, right? And so if you multiply this by the width, so W times D to the minus 1 is equal to D lambda D dx, right? I'm sorry to change that up for you guys, but, and this is, this will give you the effective bandwidth. Where W is the slit width in the in suitable units. Make sense? So basically what you can have then is you can say, well, the range of wavelengths coming out here might be, 300 to 301, and that will be your effective bandwidth. And it might be 350 plus or minus 1 nanometers. That's how you could express that, the effective bandwidth and the setting, the wavelength of the light coming out. So if you change effective bandwidth, then if you make effective bandwidth smaller, then you will see more detail in your spectrum, right? So if you've got this is 2 nanometers here along the focal plane, and if you have 2 nanometer effective bandwidth, you'll get these broad peaks. And then you can go down to 1 nanometer and you'll get narrower peaks. And this 1, when you go from 2 to 1, that's a large change in effective bandwidth. And you'll see that this 1 can transform into 2 peaks, 2 distinct peaks, right? Then you come down by another factor of 2, and you start to see a 3rd peak. And then you come down by another factor of almost 2 here, and you can clearly see this 3rd peak, right? And so when the effective bandwidth is at a 1/10 of a nanometer, right, it's a factor of 20 lower than it was up here, then you can clearly see that there's what looked like 1 peak is actually 3. And so this could easily resolve, say, the existence of a different chemical species, or give you more details about a given species or something like that. And there's often an advantage to moving to higher resolution. However, there's also a disadvantage. And the disadvantage is that as you decrease the slit width, if you say go down by a factor of 2 here, you will probably go down in intensity by a factor of maybe 8. It's just sort of a guesstimate, but that's about it. So if you double your effective bandwidth, or I'm sorry, it's actually if you decrease or improve your effective bandwidth by a factor of 2, you will decrease your signal of noise by almost a factor of 10. And that's because of spatial filtering. As you change the cone of angles that the monochromator can accept from the source, you greatly decrease the amount of light that can get into the spectrometer. You increase the purity, but you decrease the number of photons. So anyway, I'm sure there's ways around this, but for visible light, it's a tricky proposition, and you just use a bright source, etc., and you can get around it. Now, if you calibrate and you have too wide of an effective bandwidth, right? What will happen is that you'll get a negative deviation from Beer's law. And so you have to find a compromise here that works for you, because going from 2 to 0.1 nanometers is rarely possible. But I mean, if you can do it, then by all means do. But don't try to go from this green line to this dashed line, because the chances are is that you will run out of light, and the noise will overwhelm your measurement, and you will begin to lose the advantage that improving resolution will give you. So let us see. Now, a similar phenomenon happens with the acceptance of stray light. And in general, stray light, it causes negative deviations from the Beer-Lambert law, right? So if you have a calibration curve and you have stray light, the calibration curve will go up, but then it will roll over, right? It'll look kind of like this, even though this is a different plot, right? And so the absorbance error is always small when the absorbance is small. But think about it like this, right? Stray light is, if you're looking out a window and there's a lot of light coming through the window, and you're trying to judge how dark a piece of glass is, a piece of stained glass, and you put the piece of stained glass in the center of the window, then what will happen is you can put a light piece and then a little bit darker, a little bit darker, a little bit darker, a little bit darker. And when you get to a completely opaque piece of glass, there will still be a lot of light coming through the window. And so if your light averages over if your eye for example, averages over the entire window, then it won't register the diminution of light. And that will create a negative deviation from Beer's law at higher absorbance. So that's just something to look at, something to look out for. So if you have negative deviation from Beer's law at higher absorbance, then it is likely that you have stray light, or your wavelength resolution is too poor. All right, so I'm not going to do this one right now, but I don't know. Here it is. We could work this out, right? You just add the stray light into the numerator and the denominator, and it'll turn it'll give you the apparent transmittance when you know the actual transmittance is calculated from P and P0, but that's neither here nor there right now. Okay. So so let's skip this, and I would like to take a couple minutes break, right? I feel like you guys are paying attention, we're doing good, and I don't really have exercise or breakout rooms for you. I should. I'm a little bit new to this process, and so forgive me on that, but let's just take say a 5-minute break, and we will resume about 8:26, if that's all right with everybody. Okay, so I'll sign out, and then I'll sign back in at 8:26. Cool, good. Thank you, guys. So I'm back. Hopefully y'all are coming back. Let me adjust my share here. I'm gonna change to my document camera here. And basically I forgot to mention there is a third component to the sort of the grading question, right? For the grading monochrometers, and one is the grading equation to calculate calculate lambda, right? And then there's the effective bandwidth. This is to calculate delta lambda. And then there's a third consideration, which is to calculate, to calculate lambda over delta lambda. And this is called resolution. And to calculate lambda over delta lambda, you need to know the order of diffraction and the total number of grooves that you illuminate. And so this rarely limits but it can. So if you have a real small grading, like only 1 millimeter of grading, then that could limit. But if you have more than a millimeter, then it's unlikely to limit you. So we are almost ready to okay, so let's talk about filters now, and then review light sources just real briefly, and then we can move on. Does everybody have this little bit of notes down here that's on the document camera now? Or should I give you another second to try to decode my hieroglyphics? You good, Cindy?
I'm good.
Okay, great. No. Okay, all right. Oh, wait a second.
Say I'm fast. Don't go by me.
Okay,
I've learned to write with professors who write fast.
That's amazing. That's amazing. I never learned that. So with a monochrometer, you're always confronted with this little n value here, where n is the order of diffraction. And so, for example, with n is equal to, let's say I had 250 nanometers selected there, right? Or I'm sorry, n equals 1 and lambda equals 250. I'm sorry, let's say n equals 1 and lambda equals, say, 500. Then n equals 2 and lambda equals 250. That will also pass at the same time. You don't have to write that on this page. I'm sort of previewing the next thing here. So let me get the share updated here. So for example, if you have a 250 nanometer light in order 1, that will also show up at 500 nanometers in order 2, right? So if you want to see just 500 nanometer light, you actually have to filter. You need an additional optical component to remove 250 nanometers. Does that make sense, Casey? This was like what, yeah, when we did the fluorescence, we saw this, right? There was like, if we excited at 245, then when you scan out to 490, you see a peak. And that's, anyway, that's a harmonic of 245. So, you know, I'm tripping that now because it doesn't quite match the n times lambda. Should be like 2. Oh yeah, 1 times 500 equals 2 times 245. So I'm not quite sure how that shows up at 500, but I think it does. So, and it does actually. But in practice, what you need when you use a monochromator is you need filters as well. And so there's band pass and band reject filters, basically. There's long pass, short pass, band pass, and band reject filters. And for example, when we do Raman spectroscopy, we have our instrument is 785 nanometers, and we need to reject 785, right? We irradiate with 785 and we collect, and we want to eliminate the 785 nanometer light from the light that we analyze because it's there, it's more intense, but there's no information in it. And the 785 nanometer photons, if we let them go into the detector, then they will flood all of the pixels and we won't see our spectrum. It's just like there's not a perfect, like the 785 nanometer will come out like a Gaussian or a Lorentzian peak. And the tail will completely obscure our Raman spectrum unless we filter it out. Now, in order to filter it, what we'll typically use is a thing called a holographic notch filter. And a holographic notch filter is very efficient over a very narrow band of wavelength. So this is a 10 nanometer notch here. This goes from 20 to 30 nanometers. So, you know, and you can design notch filters for any set of wavelengths, and then you can make them pretty narrow also. Pretty narrow and pretty deep, right? So this goes down to, quote, 0% transmittance. It probably admits maybe 10 to the minus 4 to 10 to the minus 6 at the center of its absorption here. So that's called a holographic filter. I'm not sure how they're designed. Then they have another thing called a dielectric filter, which is closely related. They also have chemical filters. They have colored glass. And so for for a monochromator, what you'll typically use is a band pass filter, and you'll set it up so that when the monochromator setting is for, say, 250, you'll band pass 250 and band reject 500, right? And when it's at 500, you'll band pass 500 and band reject 1,000, etc. So it just sort of so that you know that filters are important in spectroscopy. So now I want to review briefly the idea of the laser. And so I want to go over that briefly. The laser and the semiconductor light detector. So as you'll recall, lasers are examples of superradiance. So let me change over to the document camera here. And so in a laser, the amplification is due to a molecular phenomenon called stimulated emission. Right. So stimulated emission is it happens when there are molecules or other quantum entities, that can absorb or emit certain wavelengths of light. When these quantum entities are present, where there's a larger population in the excited state than there are in the ground state. So if you had 100, you'd have maybe 60 excited states and 40 ground states, or 40 of the lower state in which that involves this transition, right? So stimulated emission then is m star plus h nu makes m plus 2h nu. And this is a gain expression for a laser. And then a loss expression might be m plus h nu makes m star. And this is loss, right? And then m star makes m plus h nu. This is also a loss. This is called spontaneous emission. And the reason that it's a loss is because the photon that's created is incoherent. And in this case, it's mainly the direction of the photon that's created. The direction is isotropic. So it's all directions. So The so there's absorption, spontaneous emission, and stimulated emission. And this is the only gain mechanism, is stimulated emission. And in order for there to be a net gain due to stimulated emission, there needs to be more, there needs to be a higher concentration or more excited state entities than ground state entities. So in order for there to be gain, by stimulated emission, the population of M star must be greater than the population of M. And this is called a population inversion. And population inversions are possible when M is not the ground state. Okay. So the ground, so that means that lanthanides with 14F electron orbitals, oops, make good lasers. Because it's very possible to have say more M star than M when M is not the ground state.
You have to move the paper up a little bit.
Thank you.
Thank you.
I know at least one person. Actually, I know that at least two people are paying attention. And Fook, I think.
I'm here.
Yeah, you're here. Oh my gosh.
Yeah, I need to catch up.
Oh, let's see here. I think Van is here too.
Yes, I'm
Right,
here.
Van?
Yes, I'm here.
I knew you were here. I knew you were here. And Solomon and Gianluca is sort of here, although he's super tired. And he's sort of groggy. Is that right, Gianluca?
A little bit.
Oh yeah, okay. That's not bad.
7 in the
Nicholas
morning.
is here. Yeah, I know. It's pretty early, huh?
Here.
Good. Karen's here, Solomon's here, Michael's here, Brandon's here, Mina's here. Alrighty, guys. Well, that's all I got for you today. Only one other thing I'd like to say is that the homework for this should be due in like a week from tomorrow, definitely not tomorrow. So if there's any suggestion that the homework here is due tomorrow, then please ignore that. It's a week from tomorrow. Is that y'all's understanding of it?
Yeah. Now I understand.
Okay, good. Alrighty, guys. So I will see y'all in a bit. I've got to get lab ready and stuff, but
Okay.
thanks for your attention. And yes,
T-
sir.
Will you still have office hours?
Yeah.
too?
Yeah. I have office hours today
Do you
at
mind
12:30 to 1:30.
if I might? Is it possible if I meet you at 1:30 instead because I have a PCAM course at your office hours? during your
Sure, absolutely. Come by at 1:30, no problem.
Okay.
I'll
Thank
put
you.
you on my calendar. Okay,
Thank you
great,
so much.
good. Okay,
Thank you.
bye everybody.
Dr. Terrell, could I ask you a quick question?
Sure, Mike.
So I was going over the Ramon data workup, just to, like get ahead. And
Yes.
when I was doing my numbers, my coefficient for toluene was negative, and yeah, so my
Oh,
data looks a little wonky. So like compared to
looks a little wonky.
compared to your
Huh.
graph that you did in the example in that video, it's almost like I have something below the x-axis.
Right. Okay, so what you can do is you can cut off the first 50 data points.
Okay.
And see if that helps. Because the first 50 data points are noise, and they actually detract from the accuracy of that analysis.
Mhm.
And then and send me an email and complain bitterly that science and physics don't work, and I'll see what I can do about it.
Okay.
I have a direct line to the science gods. And when they stop working, I can complain. But I need to hear from you guys.
All right. Sounds good. Thank you, Dr. Terrell.
Excellent.